Hello and welcome to today's lesson where we're going to look at sound waves, which is part of the waves topic in GCSE Separate Science Physics. So if we're successful and we learn in today's lesson, we should be able to understand what sound waves are. Now if you're successful and you learn in today's lesson, you should be able to define what a sound wave is, observe how sound waves are seen and described, and look at how sound waves are detected by humans, which falls into the following part of the AQA Separate Science Physics topic of waves 4.6.1.4 sound waves. So one of the most obvious examples of waves that we encounter in the real world are sound waves. However, we encounter them so much that we forget that they transfer energy without the net movement of particles like all waves do. So sound is a mechanical longitudinal wave. The matter which is being oscillated is the air particles. So the air particles have no net movement, only oscillation. So the idea is that the sound wave is an oscillation of matter, the air particles. If you place an object in a vacuum, an area with no particles, then it's not possible to have an oscillation, therefore we do not hear a sound wave. Now, parts of sound waves where the particles are spread out is called the rarefaction, whilst parts of the sound wave where the particles are close together is called the compression. Now remember, in a sound wave the particles do not move, only the energy is being transferred. Now, sound waves are also longitudinal waves. These are sound waves which vibrate parallel in the same direction as the direction of energy transfer. Now the posh name for energy transfer is propagation. So any longitudinal wave, whether it be a sound wave or another type of longitudinal wave, has vibrations parallel in the same direction as propagation. Now sound waves are mechanical waves, so they're oscillations of particles in the air. So sound is made when something vibrates. For example, a string on a guitar in the air. Now sound travels by the vibrations moving through the particles in the atmosphere. The closer the particles are, the faster the sound wave travels. So for an object to produce a sound wave, you must cause that object to vibrate. The vibration causes the air particles to vibrate and to produce a sound wave. So in this particular example, once again, there's a vibration in the string that's causing the air particles to vibrate and produce a sound wave. Here we've got a percussion where we're causing a vibration of the air particles around this particular instrument, and that produces a sound wave. Once again, around this particular instrument, the harp, there's a vibration being caused by the string which makes the air particles vibrate and produce a sound wave. So to measure the speed of sound, we can use a method that many animals use to determine the distances of objects, and humans also do this subconsciously, which is called echolocation. So you do this by measuring the speed of sound when considering the reflection of sound waves off objects. Now the detection of objects using the reflection of sound waves is called sonar, sound navigation and ranging, whilst radar works on the same principle as sonar, except this uses the reflection of radio waves, not sound waves. So the speed of sound can be measured via reflection. So step one, a sound wave is emitted by an object. The sound wave will then travel through the air. Now the sound wave will then hit another object and reflect, but remember it takes time for step 2 to take place because it's not instantaneous for any wave, as all waves, regardless of what they are, travel at a certain finite wave speed. So when the sound wave reflects off an object, the sound wave will travel back to the emitter. The sound wave is then detected by the emitter, and you can work out the speed of sound by doing the equation speed equals distance travelled divided by time taken. But just be very careful, the distance travelled is 2 times the distance between the object and the emitter, because the wave has gone there and back, so the distance travelled is there and back. Now in this method, any material can be used for sound to travel through, but we'll just use air in this case. Now the scientific name for this method is called echolocation, the location of objects via the reflection or echoes of sound waves. So how could you reduce the uncertainty or the impact of your error in these types of experiments? Well, to reduce the uncertainty in your investigation, you use the largest values for time and distance possible, because the bigger the values, the lower the experimental error becomes, the lower the percentage uncertainty. Now we assume in this method that the speed of this wave doesn't change throughout the investigation, which indicates to us that the medium it travels through, the air, has a constant density, and that the wave travels in a straight line to and from the experimenter. Now we can't use this method to measure the speed of an electromagnetic wave in school, because it would take such a short time to carry this process out if we fired a radio wave off an object that therefore the time taken will be too small to measure accurately. So the percentage uncertainty of the measurement will be too large, so the impact of your error time in this will be very, very large. Now, if we carried out this experiment in a vacuum, what will we achieve? Well, we'll get no result because sound is a mechanical wave, so it needs air particles to travel. So if it's working in a vacuum, okay, we can't actually get a sound wave because there's no particles there to vibrate. Now, would the starting intensity of the sound wave be the same as the final intensity of the sound wave? It would not, because as the sound wave hits off the object will absorb an amount of the wave that has reflected against it. Now, the speed of sound through air measured by this method can change throughout the day because at different times of the day the air density changes. So the hotter the temperature, the lower the air density, so the speed of sound in air varies. So sound travels slower in the middle of the day as the atmosphere is hotter and the air particles are further apart. So let's just summarize what we've learned so far. To measure the speed of sound, you emit a sound wave, the sound wave will travel through the air, the sound wave will hit an object and reflect, and the sound wave will travel back to the emitter and be detected. You can work out the speed by using the equation speed equals distance over time, but just be aware that distance travelled is 2 times the distance between the object and the emitter, as the wave has gone there and back. Now, it also assumes in this investigation that the wave speed is constant and that the wave travels in a straight line. Now, sometimes it can be difficult to visualize the concept of sound waves as we can't see them with our eyes, because as humans we monitor sound waves with our ears. So we can observe the vibrations of sound waves by using a device called an oscilloscope, or to give its full name, a cathode ray oscilloscope. This is a device that displays a physical picture of a wave after the vibrations of the wave have been converted to sound waves by a microphone. Now, what happens is the microphone transfers energy from the sound wave into an electrical energy store, and then the cathode ray oscilloscope displays the electrical energy store as a wave diagram. So just to clarify this, you can get a wave diagram on your oscilloscope, which then you can work out what the wave is showing. So you can use a microphone, and an oscilloscope to observe the electrical signals produced by different sounds and find out how they depend on the amplitude and frequency of the sound wave. And you do this by using a cathode ray oscilloscope. So an oscilloscope, like we said before, is a device which displays the energy in a wave, and the axis can be altered to show this waveform easily, as shown here. Now, it's important to note that the more waves you can see, the higher the pitch. So the pitch of a sound is the number of vibrations per second produced by the sound wave. So the pitch of any sound wave is just the frequency of the sound wave, and as a result it's measured in hertz. So here is an example of high volume, as you can see on this particular diagram, and this is an example of low volume. So the bigger the wave, the higher the volume, the quieter the volume, the lower the wave. So the volume of the sound is the distance of the midpoint of the wave to the peak of the trough. It's the maximum displacement from the equilibrium position. So the volume of a sound wave is the amplitude, and it's measured in the units of the y-axis on the oscilloscope. So just to clarify what we've learned in today's lesson, that sound waves can travel through solids by causing vibrations in the solid, but it can carry out in liquids and gases as well. You just need that vibration to take place. So if we've been successful and we've learned in today's lesson, we can define what a sound wave is, understand how sound waves are seen and described, and we can look at how sound waves are detected by humans. I hope you've enjoyed today's lesson looking at sound waves, which forms part of the GCSE separate science topic, waves, and have a lovely day.